Hello and welcome to another day of Advent of Code Solutions. Today we're looking at day 7. And in day 7, we are dealing with crabs or something like that. And they're represented as positions, and so your input is going to be a series of comma-separated numbers. And the goal is to compute the amount of fuel that it's going to cost for them to all come to the same position. And in part 1, the crabs only consume 1 unit of fuel when they move, and the goal is to compute the minimum amount of fuel to meet up. Now, kind of the neat thing about this problem today is the inputs aren't that large, and so it's not out of the question to just compute the values directly. So I'm going to show you a brute force solution, and then I'm going to show you some slightly more clever stuff that you can do for part 1. But yes, let's just start with this. And so I'm going to read all the numbers in. Numbers equals int s for s in input s dot strip dot split on comma. Basically just getting rid of the white space, so the new line that's there, and then splitting on commas, and then converting those to integers. Then what we want to do is just loop over all of the possible integers. In part 1, it happens to be that the crabs will always go to one of the positions that's represented in here. That's not necessarily true for part 2, and if we're brute forcing this, I would probably try all the ones in between anyway. So we're going to do a loop over the minimum, every number between the minimum value and the maximum value. So for I in range min of numbers and max of numbers plus 1. Of course, we're going plus 1 so that we include this number. And we are going to try and compute the minimum sum of all of those values. And so if this 16.1 was moving to 14, we would do 14 minus 16, which would be -2, and that means it moved 2 units. So we're going to do the absolute value of the difference of all of those. And so minimum value equals the min of, just going to do a list comprehension since running the loop is going to be a little bit annoying here. The sum of each value, so sum of the absolute value of n minus I for n in numbers. And so this is basically just computing the amount of fuel it's going to cost to get to position I. And if we print that out, minimum value, we will see, oops, spoilers. We'll see that we get 37, which is our expected value for this. So this is, no clever bits here. This is just doing the computation directly. And so this is going to be a n squared lookup approximately. It's going to be slightly more than n squared because we're actually picking more numbers than are in this. So it's slightly more than that, but we've got one loop here and another loop here, and those multiply together to contribute to the runtime. Now I noticed a kind of neat thing about the inputs here in that the median represents the value where the difference in all of the outer parts is minimized. And so if you just use the median here, you get to the answer much quickly. So we can do that by doing import statistics, which just gives us median directly. And let's actually just do, we'll make a compute value function. We'll do compute value part 1 for sum I, which returns an int, and fortunately it just returns this. And if we were to do the median here, and I believe statistics median always returns a float, so we'll just convert that to an integer. And so the minimum value here is actually just compute value part 1 of the median. That should also give us, I can spell statistics correctly. Yeah, that'll also give us the value. So that works great for part 1. It, however, does not work for part 2. And on part 2, it's because we have a variable fuel cost. And so unfortunately, there isn't really, well, I couldn't come up with a clever way to get to this. I tried mean. Mean is very close to the right value, and for some people's inputs, it worked correctly. But mean does not work for all inputs, and so It's not super helpful, although mean is a very good approximation of the right value, so you might be able to use mean and then wiggle around near it. That's how I solved mine. But the brute force is actually fast enough for part 2, so that's what I'm gonna show you here. And I'll leave the optimization problem to you. Now, the interesting thing, and probably the part where you may have not known this, this sequence here, 1 + 2 + 3, is a very common sequence that you'll see in programming pretty often. I think the most common example of this is computing the O of n of a double-ended for loop where it compares every value against every other value, similar to something like for I in range I don't know, len foo, and for j in range I + 1 to len foo. This is an example of one of those loops where you're going to do 1 + 2 + 3 + etc. up to n amount of work. And the shortcut for this summation is something that you just kind of memorize after seeing it pretty often. It's n times n + 1 divided by 2. And you'll see this over and over. But that makes computing at least the difference here not too tough, because we can just use this formula to figure out how much fuel it would cost to move between some position and another. And so if we reuse this function here, we really just have to adjust this slightly. So we have absolute value of n - 1 times absolute value of n - 1 or n - I + 1 divided by 2. So this is our n + 1 over 2. And so now, oh, I should have written a separate function. That's why I called this P1, so that we could keep it around. So this will be P2 n times abs n - 1 plus 1, oops, minus I, plus 1 divided by 2. And for part 2, we can just, we're just going to iterate over all the possible values, and we do have to check the integers in between. We're going to do for I in range min numbers max numbers plus 1. And just do this. Compute value P2 I. And that should give us our value, assuming that I don't mess up my syntax there. Yes, and we expect 168 for that one as well. And yeah, this is also just n squared because this multiplication is approximately constant time compared to the rest of this. And this is, a ON loop, and this is another ON loop. So overall, we have n squared there. In my solution, what I did is I used mean as an approximation, and then, wiggled around near it to do it slightly faster than this. But yeah, that's how I approached part 2. I assume there's some more clever way to do this. I'm not familiar with what that is, but anyway, hopefully you found this interesting, and I will see you around for the next day.